We're going to be finishing 2.7 today, at least based on my other class we shall, and we'll get started on the beginnings of 2.8. We're going to look at just a kind of heads up on some of the things that we have covered, but not completely. If I give you this one, this is question 7, you're going to be asked, one of the standard questions you're going to be asked is to find the slope of the tangent line M at some point. In this particular question, you're being asked to find the slope of the tangent line, right? So find M at this point. Now we would use notation something like x equals a, right? And a would be -5 in this case. Now you can do this in two distinct ways. You can do the limit as h tends to 0. Since I'm picking -5, that would be at -5 add h, take away the value of the function at -5 over h. Or I could choose to find the slope with the limit as x tends to a. So what's that? There's going to be the limit as x tends to -5, f of x, take away f of a, over x, take away negative means you add it. Now this will give me the slope of the tangent line at -5. This will give me the slope of the tangent line at -5. And I'm just going to tell you what the answer is because I already found out. It's -2/5. But you're going to have to do it the hard way. And if you've already done questions in section 2.7, doesn't it take you 10 minutes or so just to do either this one or that one to get the answer? Would it, I don't think it'd be unreasonable to suggest that isn't the conjugate method going to be used? And the reason I know that is because the square root. So you'll get the answer and it'll be a number. In this case, it's -2/5, and I'm just telling you that's what it is. And for any question that you've been asked to find the slope of the tangent line at x equals a, if the fella is a fraction or a square root, there is no shortcut. You just got to do it. Me personally, I like h tends to 0 method. If they give me a choice, I always pick this one. So if they don't mention how to do it, I strongly suggest you choose this one. That's just my preference. This one will work and you'll get the right answer. It's just, I think they're harder to do when you do this version. Now there's going to be a second part. And the second part is the equation of the tangent line. At whatever this point is. Now, to get the equation of a tangent line, you're going to use that formula every time. So the minute you find the equation of a tangent line, typically part B of these questions, this is the guy you're going to use, right? Not the y equals mx plus c or whatever, but y minus y1, x minus x1. This guy is x1, the one next door to it is y1, and the slope obviously is this guy. So it's going to be y take away 5 equals -2/5. X take away a negative is the same as adding it, so that's x add 5. That becomes -2/5 x minus 2, and so y is going to be, that guy. And that's a very common question in this section. So find the slope of the tangent line at -5, doing it either this method or this one. Once you know the answer, in this case -2/5, part B, find the equation of the tangent line. Now, little algebraic issues. Can you imagine that I got the slope of a tangent line and it ends up being square root of 5? Could happen. And let's just pretend that it was at the point 1, 2, right? When I do the slope of the tangent line formula, you might think to yourself, well, what do I do about that guy? The answer is exactly what you would have done if it'd been a nice number. Multiply through by the square root. Right, it's not the prettiest answer in the world, but it is also correct. So you might think that looks wrong because there's like 3 terms, but it isn't. Isn't that just an ugly number? So it's still, you know, square root of 5x with an ugly number. So if you get your really weird answers because of that, it's okay. It just means the answer's looking ugly and we can live with that. Now, next thing is derivatives as a rate of change. So we're going to spend a few moments being like a physics class. What do you call the difference in position divided by the change in time?
Velocity.
Yes. If I had a time against position, which I'll call d of t, and I plotted where an object was at any given point in time, and I choose a point at t equals a, and I get the slope of the tangent line, which is this guy, and I do a little triangle thing, isn't that distance there to there the change in position? So I'll call it what, delta d, and isn't that the difference in time? So I'll call that delta t. Great. Delta t, change in position, divided by delta t, change in time, is called velocity. So what does that tell us? It tells me this. The slope of a tangent line can sometimes mean full title, instantaneous velocity, or just velocity for short, of a moving object. So here is a reason for finding the slope of a tangent line. In some contexts, and what are those contexts? Well, if the x-axis is time, right, t, and the y-axis is position, d of t, then the derivative in those cases, which is what the slope of a tangent line is, it's the derivative. Will tell you the velocity of this moving object at a given time, t. Let's see how that works then. Suppose I have an object and its It's that guy. So, can you imagine it might be that if I sketched it? So at any given time t, 100, right? This is a position object. So this might be, I'm at the top of a 100-foot cliff and I chuck a rock in the air. This would be the path that the rock would take on its journey towards the ground. I could find the velocity of this object, right, this rock, at any given time. All I need to do is find its derivative. So suppose I wanted to know its velocity at t equals 1 second. Then I would find its derivative, this guy. Now, since this is a quadratic, can't we use the shortcut method? Can you remember the power rule, the shortcut method? So multiply by the power and reduce it by 1. So multiply by 2 and then reduce it by 1. You get -2 and then you put an a. Now, what would -10t get you?
Just -10.
And do you get anything from the plus 100? No, it just goes away as a 0. So I want to know the velocity at t equals 1. Don't I just find the derivative at 1? And that's -2 times 1, -10. And I am getting the answer at -12. So my picture is wrong. Evidently, although I'm at a 100-foot cliff, I didn't throw the rock in the air. I actually threw the rock towards the ground. That's okay. Do you know why I had to change my picture? That's -12. Now let's say the units are meters per second. Negative is okay. Doesn't negative mean you're going towards the ground? So that's why I changed my story. You're at the top of a 100-foot cliff and you're chucking it. So after 1 second, you're about here and you're going down. I guess the other possibility is that the real curve might look something like that, right? It may go up a little bit before it goes down. What that tells me is I can find velocity at any point I like. Because once you've got this guy, can't you plug t equals 2, 22, 50, 0, any number you like, and you will get a velocity. And so slopes of tangent line, which we tend to call derivatives now. So derivatives, when it's distance against time, tell you velocity. Suppose I find a velocity time guy. What do you think the rate of change of velocity with time is? Because it's called something, right? So if I find the derivative in the context of this story, can't I be finding acceleration? Do you see that there's a use for finding these tangent lines, the slopes of them? Because if I know a position of an object, don't I now know what its velocity is? And if I know the velocity of an object, I have no idea what that curve looks like. Right? If I know the velocity of this object, can't I now tell what its acceleration is? Very helpful thing to be able to deal with. So as you're going through that last section, the rules are, if it's a quadratic, you can choose to do the shortcut method now, right? If it's a square root or a fraction, you have to do it the long way. Later on, we'll show you the shortcut for those situations, but right now you have to do it the long way. There's no other alternative. Okay, have we got any, that's pretty much what I wanted to cover in that section. Have we any questions before I move on? Because we are going to take this thing and we're going to look at derivatives as a function. What's that? Well, there's a function. If I asked you to find its derivative, we would probably say find its derivative at x equals a, right? That would be the way it would work. And we can use the shortcut. Now, the shortcut is multiply by the power and then reduce the power by 1. I'll make that 4x squared. So multiply by the power and then reduce the power by 1. And the 3 just disappears. And this would be the derivative, right? The derivative of a is 21a squared, take away 8a. Great. Now, what would f dash c be called? And don't overthink this.
The derivative at c, or x at c.
Right, and what would its formula look like?
The same as the a, but with c instead.
Yes, agreed. Overkill, I know it's stupid, but I'm doing it anyway. Wouldn't this be the derivative at x equals d? And wouldn't its formula be 21d squared take away 8d? And couldn't you keep going through every letter of the alphabet and wouldn't you essentially get very similar looking structure? So why don't we just cut to the chase here? Why don't we just call f dashed of x 21x squared take away 8x? And that's us finding the derivative at x equals x. In fact, isn't that kind of more obvious for how you should probably say it? Right. If I want to know the derivative at 7, why do I have to turn it into x equals 7, call a 7, convert all these into a so I can get a formula with a's in it, and then plug 7 in anyway? And can't we just cut the middleman out and just do the derivative rule, right? The derivative function with x's. So if I went and said to you, same question, right? Find the slope of the tangent line to this guy. But now can't I just say at x equals 2? And when I write down my derivative, which is 21x squared take away 8x, can't I just plug in 2 here? Oops. And get 84, take away 16, 68, and get the answer. Would you agree that's just cleaner, isn't it? Isn't that x equals a and then formula with a's and then switch back again? A kind of long-winded way of cutting it out. And it gives us an extra benefit. Isn't that a function? Isn't 21x squared minus 8x a function?
Yes.
Couldn't I sketch that? Couldn't I put it into my TI-84? Just call it y equals. You call everything y equals in TI-84, right? Couldn't I just call that y equals? Couldn't I call this y equals? Original function, derivative function. And that's what we actually think of the derivatives. One way to think of derivatives, right? is it's a special function that you get from the original. The special function just tells you the slope of the original curve at any given point. Well, why is that kind of helpful? Well, to me, it cuts out this x equals a nonsense, right? It just gets them out of the way. That's helpful. It also gives us some other things. So do you recognize that function? It's been a while since you've seen it. Ax squared plus bx plus c. Isn't it the general quadratic? Right. In the context here, doesn't a, b, and c just represent numbers, right? Constants, as we call them. And the variable is x. Now, one of the things that we like to know is the x coordinate of the vertex. Can you remember the x coordinate of a vertex for any quadratic when it's written in this format? Do you remember its formula? Quadratic curve, x coordinate of vertex. Come on, let's get the cobwebs out. Any start it off for me at least.
Is it the negative b over?
You've forgotten that.
Can't remember.
Negative b over, yeah. I stopped you and I think you were saying it's
Oh, 2a.
Agreed. You remember that guy? Now, when you did it, wasn't it just here's a bit of magic? The x coordinate of a vertex is negative b over 2a. So let's see if calculus can help us figure out why that happened. Do you notice that at the vertex, the tangent line is a horizontal line? That makes sense? What's the slope of a horizontal line? What number is it?
Whatever.
Horizontal line.
0.
0. Isn't the slope is 0? Right? If you're horizontal, your slope is 0. How is that going to help me? Well, let's see. The derivative function, multiply by the power, reduce it by 1. Multiply the power, reduce it by 1. And won't the plus c get you nothing? Because a plus c is like plus 42, right? It's just a number and numbers never get you anything. And are you okay about the bx being b? You know, like 7x gets you a 7. Right? It's the power rule. Now, if that's the derivative, and I know that its slope is going to be 0, then won't 2ax plus b be 0 somewhere? And if I solve for x by subtracting b from both sides, and then dividing both sides by 2a, that's how we know where the x coordinate of every vertex for a quadratic is. Isn't that elegant? That we found the x coordinate of a vertex by not going near the quadratic formula. Remember that minus b plus a minus thing. Horrible. Isn't that just clean? Boom. Derivative is 0 is where the vertex is. What's the x coordinate when that happens? The x coordinate is whatever negative b over 2a is. If I give you a time position curve, right, one of these things, and this was a moving object and it looked like that. At this top of the hill, won't the derivative be 0? And at this bottom of the valley, won't the derivative be 0? But in the context of this question, won't that mean the velocity equals 0? So if you tell me, whatever it is, if you tell me who d of t is, right, if you give me a formula for that, can I find when that object is stationary? right? When it's not moving at all. That's kind of a useful thing to be able to find, isn't it? If someone just gave you, I'm making this up, because, you know, make that a cube, make that a square, you know, something like that. If I said to you, okay, this is the position time curve for a moving object, when was it stopped? You know, when was it stationary? Before calculus became, you know, on the field, can you imagine how difficult answering that question would now become? I mean, I'm not even sure how you could find its velocity, far less when it is zero. That's why calculus is so powerful. The things it can do are really just amazingly cool. Now we're going to show you another thing about graphs. It is how to sketch the graph of the derivative function. When you are only told f of x. Suppose let's have a pretty boring curve. Y equals f of x. It's probably a cubic. Would you agree it looks kind of cubic? I'm not even going to tell you what the equation of that is. You don't need to for the job that we're going to do. We are going to sketch what the derivative, right, what f dashed of x looks like. And the only thing we got to work with is what here looks like, what the original f of x looks like. Now you might think, well, you know so little that that's probably going to be impossible to do, right? There's not enough information. But actually, it pretty much is enough. I personally draw these in two separate curves. I've seen people who have one superimposed on top of the other. And the reason I don't like doing that is that the picture gets so messy that it's hard to keep track of what's what. So by separating the original and the derivative, I've discovered through my experience anyway that it's just worked better. So how do you do it? This is your approach. Find the tops of hills and find the bottoms of valley. Would you agree that the tangent line, which is what the derivative also measures, has a slope of 0 at those two places? Right? Tops of hills, 0. Bottoms of valleys, 0. Agreed? So far, so good. Now what I'm going to do is I'm going to drop down an invisible dotted line here and here. And I know at this point here, won't the derivative be 0? So overemphasize it. Would you agree that the derivative function crosses the x-axis, right? It's 0 value at that point. And won't it also have a 0 value at that point? So far, so good. Now, back to this picture. These dotted lines have actually separated this graph into 3 distinct regions. Region 1 is everybody here. Region 2 is that chunk in the middle. And region 3 is over here. Right? So here's region 1, here's region 2, here's region 3. And we're going to look at each region and see what we can get from it. If I choose any point in region 1, any point on the curve, won't the slope of its tangent line be pointing upwards? And doesn't that make all its derivatives positive? Does that make sense? the derivatives slopes are pointing upwards. So I indicate that by shading above the x-axis. Isn't that where positive numbers live, right? Above the x-axis. Right. Now, what about points in region 2? Would you agree that the tangent lines are all pointing down the way? And that means then that the derivatives at these points, the slopes of the tangent lines, are negatives. What about region 3? Positive or negative?
Positive.
So we can shade up here. So what do I know about the derivative? Not a lot, but we got enough. Don't I know it crosses the x-axis at these 2 points because its derivative is 0? Don't I know it's positive in this place, it's negative in this place, and it's positive in this place? So what you do to finish is you draw the simplest, smoothest curve that starts here, passes through there, gets into here, passes through there, and finishes here. And does that seem like a reasonable curve to do all those things? And that is my sketch of what the derivative function looks like. Back to the original, didn't that look like a cubic? Would you agree cubics look like that? Right, x cubes look like that. What do you get if you differentiate an x cubed? Don't you get x squareds, like 3x squareds? And isn't 3x squares a quadratic? Doesn't that match exactly what you'd think it was? So if you give me a curve, and y equals f of x sketch, I can do a sketch of y equals f dashed of x, even although I don't know the equations of anybody. All I know is what the graph looks like. Helpful? Can you imagine that you could use this technique if this was a position time function and you wanted to draw an estimate of what you thought the velocity time function would look like? Wouldn't that simply be sketch the derivative function? Can you see why putting this on top of that would just be too much going on? I think separating them out, it's already messy, but at least it's a bit clearer to see what each piece is. Right, let's try the next one. Sometimes the simplest ones will be the ones that will cause you the most trouble. This curve is even simpler than the first one, yet its answer might be much more awkward to figure out. Okay, starting point. There's only one hill. You agree that at that point there, the derivative is 0. That's typically my go-to in many questions. Agree? So drop it down. I know it's 0. In this world, there's only 2 regions now. You're either on the left or you're on the right. What's the slope on the left, positive or negative? What's going on here? Positive or negative?
Positive.
Great. Would you agree negative on the other side? Nah. Best scenario. How about a straight line? Take the simplest shape that fits the bill. So don't start bending things or curving things, because if there's no information to indicate that's happening, you shouldn't really be putting it in. And that kind of makes sense. Isn't that quadratic? You know, minus 2x squared or something. Shouldn't you just get minus 4x, a straight line out of it? You know, the power rule, you go down 1 power. So wouldn't an x to the 4 get you a cubic? Right, an x to the 4 would get you like 4x cubed, you get a cubic. Can you see that step 1 down kind of thing is also quite helpful. The next one, a new problem. We haven't seen this yet. And that is horizontal and vertical tangent. Horizontal and vertical asymptotes. Almost called it the wrong thing there. Right, I'm putting numbers in this, not because the numbers are necessary, it's just, it might help you visualize on where things are happening. It wouldn't change really anything as far as my answer is concerned. So I'm going to do, or we're going to do, classic volcano vertical asymptote. You know, you might get something like that of a 1 over x minus 1 cubed, right? Something like that. Now, when you deal with polynomials, right, curves, didn't we find the zeros and use that to separate out the shape? When there's vertical asymptotes involved, we do have a different approach. What we start with is, if there's any vertical asymptotes around, drop the vertical asymptote down to the bottom. Because in this case, that vertical asymptote is going to generate another vertical asymptote. Now, on this shape, the region has been split into a left-hand side and a right-hand side. You're just going to trust me here that if the original function has a vertical asymptote, so will its derivative. So let me try and prove it to you. Would you agree that if I choose any point that gets closer and closer to that, won't the tangent line get steeper and steeper and steeper? And theoretically, at least, wouldn't it end up being vertical if you got close enough? Now, if you have a vertical line, isn't your slope plus or minus infinity? It depends if you want to go this way or you want to go that way, right? So I know that it's going to be infinite, and that means it's a vertical asymptote. So on this side here, in region 1, would you agree that the derivatives are positive and getting really big? So the fact that the derivatives are positive, I'll shade that region in. And while I'm at it, this one is negative, I'm going to shade that in. And now I'm going to use the fact as you get closer to the vertical asymptote, the derivatives get much bigger. So what that tells me is that's the shape of the vertical asymptote on the left. Right, what's going to happen is you come in from this side. Would you agree that the slope of the tangent line is negative and getting much, much bigger? So would it also make sense then that it would go that way? Do you see that an original function, y equals f of x, which has a volcano, won't its derivative function also have a vertical asymptote in the exact same location, right, x equals 3, but won't its shape be different? In this case, it's a 1 of each, right? Volcano in the original, 1 of each in its derivative. Now, the next piece is just going to be kind of argued verbally. As you choose points on this curve going to the left, right, going this way, do you notice that the slopes go 2, 1, a half, a quarter? Aren't they basically becoming almost zero? So that tells me as this guy comes down, okay, put a funny kink here, won't the derivative become closer to being zero? The y value is zero. And on this side, zero. So that's what the derivative function of this original shape looks like. You see, it's quite different looking than its f of x is. The f dashed of x has a vertical asymptote, but notice it's not at 3. Well, you might say, well, this is a horizontal at 3. Why doesn't that have one? This isn't measuring the y coordinate. That's measuring y coordinate. Isn't this measuring slope? And isn't the slope zeros at the end? Not 3. But last guy for today. The weirdest answer I think that you're likely to meet. And it starts off pretty straightforward. In case you're not sure, this is meant to be a semicircle. And we are going to sketch its derivative. And its derivative is not what you think. Starts off exactly the way it should. Can you imagine I drew this better? And right there is my 0. And I drop my little line down and the y-axis gets in the way, but I can live with that. And I've got a region here called 1. I get a region here called 2. And on this side is positive. And on this side, it is negative. And you're probably thinking, straight line, like it was with the quadratic, but it's not. So what we're going to kind of try and do is we're going to imagine little snapshots of its journey till you get to the end, which is here, right? And then little snapshots of what the slope of the tangent line would look like until you get to the end. Right. Which one? Yeah, this one. Would you agree that as you start here, if you look at this one, won't the slope be quite small? Be half. And won't the tangent line maybe be 1, be 2, be 3? It's hard to imagine, but can you trust me that if you look really carefully, a circle, when it comes to the end of its life, right, when it hits the x-axis, that at that point there, and at that point there, the circle is actually vertical. In fact, if you draw the whole circle, does it help if you see the whole circle? Can you see it being vertical now? What is the slope of a vertical line?
vertical lines. What's the slope of a vertical line?
That's undefined.
Right, undefined. But we are a little bit more detailed about what kind of undefined. Wouldn't we also say infinite? And infinite positive or infinite negative, right? Depending on the situation. Would you agree that these are all positive on this side? And so when it gets to here, it is going to be infinite and positive. Would you also agree as you travel towards, it gets smaller? So how do you make both those things happen? You go vertical and then you just get smaller. What about on this side? Well, you're going to be vertical at the end. Aren't these going to be negatives? But as you get closer,
aren't the negative slopes going, aren't the slopes, although they're negative, aren't they also going to get smaller? You probably would not have expected that the derivative function of a circle to be so strange. Agreed? It's kind of weird. Just a little puzzle. That's us for today. Say hi and bye-bye.